Let's take a look at section 2.2, frequency distributions. A frequency distribution shows how data are partitioned among several categories or classes by listing the categories along with the number or frequency of data values in each of them. So, for example, let's say that we had a list of IQ scores. We could use a frequency distribution or a frequency table to help organize those. These are the classes right here to the left. You see 50 to 69, 70 to 89, so on and so forth. And then this is the number of data items that falls within that range or within that class. All right, and so it just summarizes data pretty neatly. Um, we call the small number within each class the lower class limit. All right, they're the smallest numbers. And then the larger numbers, those are the upper class limits. Your class boundaries, this can be just a little tricky. Your book says are numbers used to separate classes but without the gaps created by class limits. If you take, like, let's see right here, what is the distance between an upper class limit and the next lower class limit? Alright, so if you look, the difference between 69 and 70, or the difference between 89 and 90, or the difference between 109 and 100 is 1 unit, or just 1. Okay? If you take that number 1, whatever the distance is between a consecutive upper class limit and lower class limit, which in this case is 1, and you divide that by 2, you get 0.5. The way that you get class boundaries now is you subtract 0.5 from the smallest class limit, smallest lower class limit, which would be from 50. So 50 minus 0.5 is 49.5. And then to get the other class boundaries, you add 0.5 to each upper class limit. So add 0.5 to 69, you get 69.5. Add 0.5 to 89, you get 89.5, and so on and so forth. Now, it's not always 0.5, but for this particular example, the distance between the upper class limit and the next lower class limit is 1. 1 divided by 2 is 0.5. So you have to figure that out, what to add or subtract or to get your class boundaries. Class midpoints, those are values in the middle of the classes, and it says can be found by adding the lower class limit to the upper class limit and dividing the sum by 2. So if I was to say 50 plus 69 and then divide that by 2, I'd get 59.5. 70 plus 89 divided by 2, 79.5, and so on and so forth. So that's how you find the class midpoints. The class width, that is the difference between any two consecutive lower class limits or any two consecutive upper class limits. So for this frequency distribution, we have a class width of 20. And you'll always have the same class width in between every two consecutive lower class limits or upper class limits. That has to stay consistent for it to be a frequency distribution. So why do we want to construct frequency distributions? Large sets of data can be summarized. So, say we have 1,000 different data items. We could take all of those and summarize those in one table. We can analyze the nature of the data, so you can see, where are your data items around most? Which class are they in the most? Are there classes, maybe the lower classes or upper classes or even the middle classes, where the data items are large or are small, and we can have a basis for constructing important graphs. Um, your book and this PowerPoint here that now goes through how to construct a frequency distribution, and so you might want to practice a little bit on that. Gives you steps on how to do that. Determine the number of classes between 5 and 20, depending on how many data items you have. If you only have 10 or 20 data items, then you may just want 5 classes. But if you have 1,000 data items, then maybe 20 classes. And then calculate your class width that you want to use. Maximum value minus minimum value divided by the number of classes that you've chosen. Create a starting point. So choose a minimum data value or a convenient value below it as the first lower class limit. Then we need to use the class width to get the other lower class limits. List the lower class limits in a vertical column and proceed to enter the upper class limits. Alright, I've had a question before on this next step. Take each individual data value and put a tally mark in the appropriate class. A tally mark, if you see that in your text or on a homework problem, it's just like a little, you'd put a little mark, like just one mark for each data item if it's in the class, and then you add up all the tally marks. So, maybe you have a bunch of straight lines, you just add them all up, and that's how many data items you have in that class. Relative frequency distribution, that's the same as a relative, or I'm sorry, it's the same as a frequency distribution, but instead of the frequency, you put down a percentage, or you put a proportion, like a decimal, or something like that. So if you use a relative frequency, then you'll say the class frequency divided by the sum of all the frequencies. If you use a percentage, you do the same thing, except you just say it times 100%. So this is the same table that we had earlier. This is, let me go back to the slide. This is this table. Okay, it's just a little different. Here's the relative frequency. So instead of just saying there are two, what we can do to make a relative frequency chart is you say 2 divided by, and now sum all these frequencies up. So if you sum all these frequencies up and say 2 divided by that, you'll get a decimal. Say that decimal times 100%, and you'd have 2.6% or thereabout. It looks like they rounded to one place. And you do that for each one of these. Take the number divided by the total, number divided by the total, and you get the different percentages. That's a relative frequency. Cumulative frequency means that we have 2 in this class. Now with this next class here, it would be 2 plus 33. That gives us 35. 35 plus 35 gives us 70. 70 plus 7 gives us 77. So it's getting larger and larger and larger because you're adding up each frequency as you go down. And usually here on the left where it has 70 to 89, you wouldn't have that. You would have something like, let's see, instead of 50 to 69, you'd have like below 69 right here, and that would be 2. And then below 89 would be 35. Below 109 would be 70. Below 129 would be 77, and then below 149 would be 78. So you don't keep the same classes here if you do a cumulative frequency. In later chapters, there will be frequent reference to data with a normal distribution. One key characteristic of normal distribution is that it has a bell shape. Frequencies start low, then increase to 1 or 2 high frequencies, then decrease to a low frequency. The distribution is approximately symmetric, with frequencies preceding the maximum being roughly a mirror image of those that follow the maximum. So what it's talking about is, if you were to look at this right here, this is approximately normal distribution because you start out with low, then you get up to near the maximum amount, and then you start going lower again. And this isn't, precisely a bell-shaped curve if we were to look at it, but this is, a normal distribution, or because you start out with low numbers, you get larger, and then you go back down to low numbers. That's what a normal distribution is all about. Gaps. The presence of gaps can show that we have data from two or more different populations. However, the converse is not true because data from different populations do not necessarily result in gaps. Alright, so let's look. The table on the next slide is a frequency distribution of randomly selected pennies. Alright, so here's a frequency distribution of the weight of pennies. Alright. The weight of pennies in grams are presented, and examination of these frequencies suggests we have two different populations. So, you see these right here, there's a lot that weigh this amount of grams, and then there's none that weigh here, there's a bit, that's the gap we were talking about on a few slides back. And then you see these right here, the other pennies are weighing a lot more here. So this must be like from two different time periods. It says pennies made before 1983 are 95% copper and 5% zinc. Pennies made after 1983 are 2.5% copper and 97.5% zinc. So you can see a big difference there. And that finishes up section 2.2.